So let us move with the smart class presentation of this chapter electricity and revise all the concept that we have taught in the previous classes.
An integral part of our lives. This is because it can be used anywhere and everywhere and for various purposes. Electric current arises when charges flow from one place to another. But why do these charges flow? Let's look at an example to understand this. Consider two vessels, A and B. Let's assume that the water in vessel A is at a higher level than the water in vessel B. Now if you connect these vessels with a pipe, you will see that the water flows from vessel A to vessel B till their water levels equalize. Similarly, electric charges move from a point with a higher potential to a point having a lower potential. Look at the two metallic spheres. If you connect a metallic wire between them, electrons begin flowing from sphere B to sphere A. This flow of charges is called electric current. Because electrons flow from B to A, the flow of electric current should be from B to A as well, right? But it's not so. That's because when electric current was discovered, it was assumed that positive charges move to cause current. So even today, electric current is conventionally believed to flow from the positive end to the negative end. That is why the positive terminal is said to have a higher potential than the negative terminal. The difference between the electric potentials is called the potential difference. Now, let's see how current flows in an electric circuit. Here is the most basic electric circuit. It has an electric cell, a light bulb, switch, and of course, connecting wires. The cell is the circuit's driving force. That's because it creates the potential difference that makes electric current flow through the circuit. The switch helps us connect or disconnect the circuit anytime we want. Let's switch on the light and see what happens. Notice how electrons move out from the negative terminal of the cell, travel through the entire circuit, and come to the positive terminal. And now, see how conventional current flows in the opposite direction. Current is defined as the rate of flow of charges. Simply put, current is a measure of how fast charges flow through a circuit. To measure the current flowing through a circuit, connect an ammeter in series. Use the unit ampere to express electric current. 1 ampere of current is equal to 1 coulomb of charge flowing through a circuit in 1 second. Potential difference is defined as the work done to move a unit charge from one point to another. To measure the potential difference across any two terminals in a circuit, just connect a voltmeter in parallel across the two terminals. Express potential difference with the unit volt. 1 volt of potential difference is equal to 1 joule of work done to move 1 coulomb of charge.
Voltage, current, and resistance. A circuit is a closed loop through which electrons travel. A source of electricity, such as battery, provides the electrical energy within the circuit. Batteries will contain a certain number of volts, the voltage being a measurement of its electrical potential. In other words, voltage is the measurement of the energy carried by the electrons in the circuit. Voltage is also referred to as potential difference. 1 volt is 1 joule of energy per coulomb of charge. The units of voltage are volts, named after physicist Alessandro Volta, who developed the earliest battery, and they are represented by the symbol V. We need to remember that voltage is just potential. To do any work, the electricity must first flow through a conductor, such as a copper wire. If we use copper wire to connect the positive side of the battery to a light bulb, and then complete the path by connecting the bulb to the battery's negative side, an electric current will flow, and the bulb will glow. Electrons carry the energy produced by the battery. As more electrons move through the circuit in a given period, more energy will be carried across. This path through which electricity flows and does some work, in this particular case, lights the bulb, is referred to as a circuit. The rate at which an electric charge passes a point in a circuit is known as the electric current, identified with an I. Electric current is measured in amperes or amps, which is abbreviated as A, named after the French mathematician and physicist André-Marie Ampère. As electrons move through the wire, they will experience resistance. When any material resists the flow of electrons, the energy will be released in the form of heat. Once the temperature of the resistor reaches a certain point, some of the thermal energy will be converted into light energy. Incandescent light bulbs work on this principle. The filament of the light bulb will be highly resistant, glowing when current passes through it. Resistance is denoted by an R. The unit of resistance is an ohm, named after the German scientist Georg Simon Ohm. The symbol for ohm is the Greek omega. Summary.
What happens when two vessels containing water at different levels are connected together through a tap? When the tap is opened, water flows from the vessel containing water at higher level to the vessel containing water at lower level till the levels in both the vessels are same. Water levels are subjected to hydrostatic pressure. When the pressure equalizes, the water stops flowing. Just as flow of water Electric charges can also move from a point having a higher electric level to a point having a lower electric level. If a metallic wire is connected between two electric levels, then electric charge flows through the wire. This flow of electric charge is called electric current. The conductor having excess of electrons is negatively charged and said to be at a lower potential, while the conductor having deficiency of electrons is positively charged and said to be at a higher potential. The difference between the electric levels is called as the potential difference. When, after some time, both the conductors will acquire electric equilibrium, they will have equal potential and no charges will flow. Therefore, there will be no electric current then.
So current and potential difference concept you understood, I think, after looking the videos.
Electric potential difference. Any source of electricity, such as a battery, provides electrical energy. When the two terminals of a battery are connected by a wire, electrons will flow from its negative terminal toward the positive terminal. Batteries contain a certain number of volts, the voltage being a measurement of its electrical potential difference. In other words, voltage is the measurement of the energy carried by the electrons in the circuit. Voltage is also referred to as potential difference. 1 volt is equal to 1 joule of energy per coulomb of charge. Batteries have a specific potential difference in their charges. A D-cell battery with a potential difference of 1.5 volts means that every coulomb of charge moving from the negative end to the positive end will do work equivalent to 1.5 joules. A smaller battery, such as a 1.5 volt AA, will also do the same amount of work. The difference between larger and smaller batteries is that a larger one contains more of a charge and consequently will last longer. The electric potential difference is the work done per unit of charge to move the charge between 2 points against a static electric field. The equation for potential difference can be written as V is equal to W by Q, where W is the work done and Q is the charge. Let's calculate the potential difference between 2 points. If 2500 joules of work is done to carry a charge of 60 C from one point to another, work done W is equal to 2500 joules. Charge Q is equal to 60 C. Potential difference V is equal to W by Q, which is equal to 2500 joules by 60 C, which is equal to 41.6 volts. Summary.
So let us move to the question, some question answer of this topic. Tell the answer. Quickly, one by one, tell the answer.
Potential difference. Potential difference is applied to it.
Correct, very good. Next. Calculate and tell quickly.
Option D.
D. Correct. Quickly tell.
Sir, option C. C option. Sir, option C. The 220 volt. 46.
It is 220 volt. Zero potential.
Sir, 10 to the power minus 3.
1
3.
milliampere is 10 to the power minus 3 ampere. So
Yes.
1 ampere is 10 to the 3
Yes.
milliampere.
Yes, sir.
Everyone tell
Potential
answer.
difference. Potential.
Arunjati is saying, I think. Siddharth, you are there. Saurabh there. Pratish Ranjan also tell. Everyone. Devan, Smile. Priyanshu, Sanskar, Smriti Ranjan. What you are doing there? Answer. One kilowatt hour.
3.6 into 10 to the power 6 joule. Option A. C also.
C also. 10 coulomb charge. It's very easy. Fatafat. Quick little. Multiply and tell W equal to V into Q.
Yes, sir.
Joule by coulomb, W by Q. Work. Now V
Work.
equal to W by Q. Potential difference. V equal to W by Q. Electric potential difference applied in the circuit is doubled.
Sir, double.
Sir,
The
electric
potential.
power.
Is wrong. Joule by coulomb. Second is there. Options are not there. Okay. So we'll move to the next topic. Let's now learn about circuit components and their representation, and then Ohm's law, factor operating resistance. What is a circuit diagram? Let us see.
Circuit diagram. A circuit is a closed loop through which electrons travel. A source of electricity, such as a cell, provides the electrical energy within the circuit. The cell will contain a certain number of volts, its voltage, a measurement of the electrical potential produced by the cell. However, voltage is just potential. To do any work, the electricity must first flow through a conductor, such as a copper wire. The positive side of the cell will have a higher voltage than the negative side. If we use copper wire to connect the positive side of the cell to a light bulb and then complete the path by connecting the bulb to the cell's negative side, an electrical current will flow and the bulb will glow. This path through which electricity flows and does some work, in this particular case lights the bulb, is referred to as a circuit. As electricity flows from the positive side of the voltage source to the negative side, electrons will move in the opposite direction from the negative end to the positive. Unless the circuit is complete, that is, from the voltage source, make a full circle back to the source, electrons will not move. A circuit can be represented diagrammatically with several symbols. Let's look at a simple circuit diagram. The voltage source, in this case a cell, will be represented by alternating long and short parallel lines. The longer line indicates the positive terminal and the shorter the negative. A single cell will be represented by one long and one short line. A wire or conductor will be depicted by a straight line. A resistor, which is a device that resists electrical flow, will be indicated by zigzag lines. A resistor may also be a light bulb. A switch, when open, is represented by a broken line and when closed by a connected line. Summary. A circuit is a closed loop through which electrons travel. A cell is represented with alternating long and short parallel lines. A resistor is indicated by zigzag lines. A switch, when open, is represented by a broken line, and when closed by a connected line.
In 1826, George Simon Ohm stated a law establishing the relationship between voltage and current in an ideal conductor. Before we state the law, let's see what it means in practical terms. For this, you will have to conduct a small experiment. You'll need a thick coil of wire, 4 electric cells, an ammeter, a voltmeter, and a switch to control the circuit. Click the switch to turn it on. See how the pointers of the ammeter and the voltmeter moved. Note down these readings in the observation table. Vary the voltage of the circuit to see how the current reacts. Drag another cell to the circuit. Click the switch to turn it on. Note the change in the ammeter and voltmeter readings. Jot down these values. Again, change the voltage of the circuit to see how the current reacts. Drag another cell to the circuit. Click the switch to turn it on. Note the readings in the table. Again, increase the voltage of the circuit to see how the current reacts. Drag another cell to the circuit. Click the switch to turn it on. Note the readings in the observation table. Take the independent variable, that is voltage V, on the x-axis and the dependent variable current, I, on the y-axis. Plot the points to find out the inverse ratio of V upon I. If we plot current against voltage on a graph, we get a straight line. This shows that as the voltage is increased, the current also increases. Also, look at the ratio of voltage upon current. What do you see? The ratio is constant. This constant value is called resistance. Resistance of a wire is always constant at a given temperature, provided the physical state of the wire remains the same as well. Now, let's try and sum up all the information. We saw how current changes with a change in voltage. It shows how current and voltage in a circuit are directly proportional to each other. We've also seen that V upon I is a constant called the resistance of the wire R. From the equation, we get V is equal to IR. This is the relationship that George Ohm summarized in his law. Ohm's law states that the current flowing in a conductor is directly proportional to the potential difference across it. We know that the ratio of voltage by current is called resistance. But what does resistance mean in the real world? Moving electrons create current. As these electrons flow through the circuit, they collide with the atoms of the wire. Due to these collisions, the motion of the electrons is hampered. This opposition to the current is called resistance. A metal in which a large number of collisions take place will have a larger resistance. If you look at the equation of the Ohm's law, you can see that the magnitude of current depends not just on voltage, but also on the electrical resistance of the conductor. Simply put, for a fixed voltage, more current flows through a wire of less resistance than through a wire with high resistance. Ohm's law describes voltage, current, and resistance. If you know any two of the values, you can find the third. Use the Ohm's law circle to help you with this. Just hide the physical quantity you need to find, and you get the formula. Take a look. V is equal to IR. I is equal to V upon R. R is equal to V upon I.
The resistance of a conductor depends on many factors such as the material from which it is made, its length, and the area of its cross-section. Let's check this with an experiment using a wire as a conductor. Here's a basic circuit with a battery, a key, an ammeter, and a resistor, that is, a wire. You can change the material, the length, and the diameter, that is, the area of the cross-section of the wire, and see how its resistance changes. The resistance of a conductor also depends on the ambient temperature. In this experiment, the temperature of the lab remains constant at 20 degrees Celsius. First, let's see how the resistance of a wire changes with its length. For this experiment, the diameter of the wire will remain constant at 0.2 millimeters. First, select the material of the wire. Now, select the length of the wire and click Start Experiment to close the key and note down the ammeter reading. Repeat the experiment using different lengths of the wire. Now, let's see how the resistance of a wire changes with its diameter, that is, the area of its cross-section. For this experiment, the length of the wire will remain constant at 100 meters. First, select the material of the wire. Now, select the length of the wire and click Start Experiment to close the key and note down the ammeter reading. Repeat the experiment using different lengths of the wire.
So you can see the ratio of V to I, it will decrease with increase in area in this case. Okay. So I am giving some question. You have to write the question in your copy and you have to write the answers. I will send the recorded video. It is impossible to discuss now. So I will go through the questions and write the answers in your copy. And after showing the question, I will end the class here. It is
Thank you,
recorded.
sir.
I will send.
Yes, sir.
Sir, can we leave?
Yes, you can leave. Thank you, everyone.